the whole first half of calculus is about finding derivatives. So we want to start by understanding where or when, under what circumstances, we won't be able to find the derivative of a function. So there's 4 places where a function could fail, will fail to have a derivative. And that's at a corner. We've seen a function like this before, maybe in your function notebook. At a cusp. At a vertical tangent. Remember, derivative means slope. So if the slope doesn't exist, then the derivative can't exist. Or at a discontinuity. So you'll want to draw in a little picture of each of these 4 different possibilities. Most of the functions we study will be differentiable. Like I say, we won't be able to find derivatives, which is our whole job the first semester, if the function's not differentiable. So at the top of that last slide, we said that you're going to be able to find a derivative wherever the function is smooth and continuous. I call that the baby brother definition. And you can use it, but it's not a justification. It's not a calculus justification for where or when a limit exists. So we do have a formal definition. You'll want to make sure this goes on your blue paper, and it also goes into your notes. So a function is differentiable at a point C, if and only if the limit as x approaches c from the left of f of x minus f of c over x minus c equals the limit as x approaches c from the right of f of x minus f of c over x minus c. So a function is differentiable at x equals c if the limit as you approach c from the left of the derivative equals the limit as you approach c from the right of the derivative. Essentially, the slope as you come at the point from the left has to equal the slope as you come at the point from the right. And 2 quick theorems that just follow from differentiability. We know that if for a function to be differentiable, it has to be continuous. So we can therefore assume that if you ever find a function and you know it has a derivative, you can assume that function was continuous. So if f has a derivative at x equals a, then f must have been continuous at x equals a. And this other one, we call this the intermediate value theorem for derivatives. It doesn't come up nearly as often as the intermediate value theorem that we've already talked about, but it's good to have in your notes. It's really just an application of the intermediate value theorem to the function f prime, the derivative of f. So if a function f is differentiable, so it must therefore be continuous. If a function f is differentiable, then its derivative has to take on every value between its derivative at a and its derivative at b. So this picture can help. Here, f prime of a equals 1/2 means that at x equals a, the slope of the graph is 1/2. F prime of b equals 3 means that at x equals b, the slope of this graph happens to be 3. So the slope at one place is 1/2, the slope at another place is 3. That means somewhere between a and b, this function has a slope of a tangent line, a derivative, that is equal to every possible value between 1/2 and 3.